Good afternoon, everyone. Thank you for coming to Share by Defense. The headline of this defense is actually made up of two parts that this project consists of. And overall project is dealing with timing issues in the vehicular environment. And one part of it is dealing with timing issues using cooperative sensing. And the other one is trying to, we actually came with a new system approach for multi-band energy-based sensing. So, in big picture, I will give first the motivation why we're even doing sensing in the vehicular network. And then we'll go with part one and part two of the overall project. So vehicular networks have been for a while envisioned as an infrastructure to empower numerous applications in vehicles and infrastructure itself. So one of the things that is challenging in vehicular networks is their dynamics. So we would say, having this dynamics in mind, why would we want to do sensing in vehicular networks? In licensed band, we would want to help deal with network congestion because mechanisms in place do not, as some work in WINLAB has shown, mechanisms in place do not meet quality of service requirements for vehicular networks, and especially CSMA with congestion control would be inappropriate because first thing when the spectrum becomes unavailable, first thing that fails is the broadcast mechanism because it doesn't have a handshake mechanism. So,
can you define sensing for me? Are you sensing parking spots or potholes?
We are sensing spectrum, looking for...
Show a picture.
Come again?
Show a picture.
Actually,
The picture is later.
yes, it is later for...
What's the output of your sensing? Your sensing mechanism?
This... the product has two parts, kind of depending on the parts, the outputs are different. In first part, we're dealing only with one channel, and the output is decision channel is available or not. So the output is decision available or not available.
Okay.
In the second part, we're dealing with multi-channel, so we have a vector of channels, and then we have a vector of channel availability, which has zeros and ones. Zeros where the spectrum is not occupied, and ones where it is.
That's all you want.
So, reasons for sensing in unlicensed band. There are projects in place exploring how we can use TV bands to utilize them in vehicular networking. To be able to use it, we need to first sense to know which channels are free. Challenges of networking, of vehicular networking, fast changing environment, and fast sensing, because we don't have time in this fast changing environment to sense as long as we want. This thesis in general is dealing with this issue. We are dealing with timing issue, how we can achieve certain performance in certain time. So, looking at a quick example of what we do, if we assume that one color and of cars and infrastructure is one application that's in place, either vehicle to vehicle or infrastructure to vehicle, then adding new applications and to existing environment would in general result in spectrum unavailability. We are suggesting here, if we know which bands are occupied and which are free, applications and users can move to the bands that are not being utilized. So for the first part, we say the performance of an energy detector is known. That's what it is. It depends on certain parameters. And we want to say how much would a cooperation between different sensors contribute to the performance of the sensor. So I'll give a first system overview of what we did, analyze single sensor performance, and then see what we did on a cooperative part. So for a single sensor, if we concentrate on a single band, square the samples and integrate them, and do some thresholding, it's a standard energy detector. The performance is known, and what we know that the performance depends on received signal level, on observation time. The higher the signal level, the better the performance. The longer the observation time, the better performance. On observed bandwidth, the larger the band, the wider the bandwidth, the worse the performance, and availability to accurately determine the noise level. So, what I plotted here for looking on a sensing time, because here we focus on a timing issue. Looking at a sensing time and probability of miss for different, I plotted probability of miss for different bandwidths. And as we can see, the larger the bandwidth from 100 kilohertz to 10 megahertz, the higher the probability of miss, the worse the performance.
How does this sensor model compare to what's implemented in 802.11 right now?
Come in?
How does this compare to what's implemented in 802.11p right now?
What they currently have in place, I'm not actually fully aware of what they currently have in place for sensing part.
Would be an interesting comparison to make.
It would be, yeah. I mean, here we follow.
So this model that you have, what exactly does it do? Can you fast build it?
Yes.
And then
We assume here one big assumption that I didn't mention is that signal is permanently present. So we assume.
So then you create a waveform to
Yes.
get rid of the negative part.
Yes.
And
Integrate them for a while of sensing time.
what's the last part?
The last one is thresholding, comparing to the observed result comparing to a threshold, which would be somehow determined noise level.
I think if you're referring to CSMA has a complicated algorithm which includes energy detection as a first step, and then the second step is trying to correlate with the incoming front-end sequence, and then using some other complicated scheme making the decision whether this packet is the right packet. Sometimes you don't have to use all three.
I can sort of look at this as the performance of only the energy detector part.
Right, only the energy detector part, and also like the question is, what is the timing, right? How much time do they use and all these things? And what's the bandwidth? And in their case, they have 20 megahertz, and the question is, what is the time that they integrate and so on.
So how did you choose the parameters here?
It was just for informative purposes. That's why we went from 100 kilohertz, which would be
Thresholds, for example, you need some threshold up there, right?
So how do you choose the threshold? What is the PFA?
Yes, from the PFA, I think it's 0.01, pretty sure, on it, starting with assuming certain temperature, certain I mean, we assume that we know what the noise level is at a certain temperature, and saying yes. For this,
He chose probability of false alarm to be 1%, which is, you can argue that's a good number, but it's a good reference. So that gives a threshold rate.
yes. And then from
And what is the relationship here with bandwidth? Why do you get higher miss rates?
higher miss rate, the higher the bandwidth, the larger the bandwidth, the higher the miss rate because more noise is getting practically introduced by having larger band.
What do you define as a miss?
Miss is if we assume that the signal is there, we missed it. If we say it's not there.
The signal is there, but the detector says it's not there.
One minus probability of detection.
If there's more noise, wouldn't there be more energy in the channel?
Well, he fixes an energy to the. What's your question?
If there's more noise, wouldn't there be more energy in the channel and the detector then if it's thresholding on energy would say always busy?
So the assumption is that he fixes the power or energy of the signal for a fixed distance. So the bandwidth of the signal may be changing, but the energy of the signal is fixed.
And you're also background.
Yes.
But the energy of the noise gets added to the signal.
The energy of the noise goes down with bandwidth. That's why it's
It goes down with increased bandwidth or it's what? Goes down with less bandwidth.
yeah, noise is proportional to the bandwidth. So the SNR, he's not comparing a fixed SNR, he just fixes the energy of the signal.
So is there some threshold here relative to the noise level? You sense the noise level
Yes.
first and then
So we say we know the noise. The assumption is that we know the noise level.
now I get it.
I guess you can sort of say here, assume that a transmitter can transmit a certain power, right? Which bandwidth of the signal would you choose? If you're at a certain distance. That's
So,
what you can
I mean, our thing was if you have 1 to -4 seconds available, depending on what probability of miss you want to achieve, that's with how wide band you can go. That was the information that we wanted for this.
What is that 10 to the power of -2?
-2, 3, 4. Yeah.
Do you have a reasonable upper bound on what the noise score could be for the band area?
What's the question?
Do you have a reasonable upper bound for what the noise, because your band is limiting, your passive band pass filters are limiting how much possible noise you can treat it as white, you say.
He assumes white noise.
Yeah, so if you treat it as white, then it passes through the band colored, and then there's some flat function. There should be a sort of a threshold of power that you would expect.
I think he assumes an ideal bandpass filter, so the band is still flat.
Okay, we should let him move on.
Yeah, it is true. I mean, this is actually just it's not even a simulation, it's an analytical result. So what we do here, we say, if we have one sensor, so looking at this will be the performance of a single sensor. That's how good it can do in these circumstances. And then we say, okay, let's assume if we can make these sensors cooperate, how would that work? And cooperative sensing has been extensively researched over the past several years because it was seen as a potential of providing good results for improving overall performance of sensors. So what we here do is we say, because it's vehicular, we're not gonna go with complicated cooperative schemes. We're just gonna go with simple ones, logical ones, where the sensors send to fusion center their decisions, zeros or ones, or they send the measured values, which are then just added up in the fusion center. So we go with simple, and it's known that performance of a cooperative technique depends on fusion technique, which is in place, and on the sensor topology. Our motivation was having in mind that we can emulate certain topology for vehicular environments, and we know what the vehicular channel looks like. Let's see how these cooperative techniques actually perform in these circumstances.
So is there any view of how this fusion center could be realized in practice?
Well, I didn't give it too much of a thought. This is more of a assumption. Let's see what would it be like if we had it.
Well, you can make arguments, right? What's hard fusion, what's soft fusion, how much. A fusion center can be any one of the sensors, right? Any one of these cars could be a fusion center. It doesn't have to be somewhere centralized. You just have to make a network.
To fuse, you have to have some information from the other cars. Right?
Yeah, you have to combine it. You have to have a control channel work sort of like along the ideas of race infrastructure.
How would you do that? So you have a control channel where you exchange the information.
Yeah,
about
but
the
it's
other
a
channel?
very low rate, very low channel because it's you just try
But
different.
the availability changes every millisecond.
Why? Well, depends.
Transmissions.
So I think
It depends.
The scenario they're looking at is a bit straightforward, that you have 8 to 11 feet on these,
Right.
and you're trying to do wideband sensing or whole Northcote spectrum or something like that. So you already have a 8 to 11 feet unlicensed band functioning, and out of that there's a significant bandwidth which is dedicated for control. You can define a control package to be my spectrum reading this or whatever.
But you're sensing the 8 to 11 spectrum yourself.
No, you're not sensing. You're not doing that. I think what they're
Then what are you
doing-
sensing?
So they're sensing
You assume that
other,
it's on the radio and it's
they're sensing other blocks of spectrum to make kind of macro decisions on what spectrum is available or not. But I don't think that problem, the engineering problem was not completed, so I think there is Onur has a particular model in mind which might be different from what, I mean, he should have answers to those, but I think it's sort of an
It's a
abstract.
challenging task. If you could, I mean, it's a changing environment.
Before you tell me that it's a challenging task, you have to tell me what that task is.
The task is, well,
Problem is-
the task of having cooperative vehicles cooperate to get a valid sensing decision.
Yeah, but I think you could ask the question that
Spectrum.
Spectrum
What-
sensing.
what-
I'll come
what-
to that picture.
for what purpose?
Marco is raising the question that suppose they did cooperate, and if they already have a 8 to 11 P channel, then why do they care about other spectrum? Is it like load balancing and later you move some channels to this new spectrum, or do you create a new video service between the cars that is wideband cognitive? You have to kind of be able to explain those.
Okay, I agree. So, I mean, the motivation of why perform sensing in vehicular networks in general. I started with it, and one of them would be to deal with network congestion. Even having in place techniques that are there to avoid congestion of packets in a packet-based network, adding new applications and new users will bring congestion up. So we are
On the control
advocating
channel or another
Sorry?
channel? On the control channel or another channel?
or all channels, or any channel.
So I think you should be a little more clear about the scenarios. I can give you a plausible scenario that some cars are moving around and there's a tower to which they want to send massive photographs, and 8 to 11P would get congested, but the spectrum sensing, you pick this thing and use a cognitive radio to do a whatever 100 megahertz its transmission. So that's a secret, but you have to be able to articulate this.
See, Dusan, that sort of goes along the lines of what I was always telling you. You need to have some sort of numbers because it's some realistic system which you sort of were reading, but kind of like you never really got to. These are the balance, these are the systems that we care about. You stayed in the abstract a lot. But, for example, like, you have later, you're talking about 6 megahertz band, so he's looking for a TV channel which is available, and he could have a control channel for these rates. The TV channel doesn't change much. Maybe you go beyond. So, you need really low rate band somewhere else to sort of communicate between cars to agree whether the TV channel is free or not. Right? And what's the key is to see, if you're behind a truck, you don't see the tower, and
if it doesn't change much, you could also just use a longer sensing time on one car.
Say again?
If it doesn't change much, you could also just use a longer sensing time on a single car.
Well, that could be the case if the environment didn't change. The thing is, like, the TV signal might be there, but there might be a truck which blinds you. And that's why I need other cars to help you confirm that there is a TV signal.
Okay. I would agree. I mean, we did say in a bit abstract world, in a sense of not actually exploring the exact numbers, because we were kind of hoping that Theodore would be the one who would give us the application requirements. Even for probability of false alarm, we could not come up with a feasible agreement on what would be the good ones. So
at some point you have some slides which talk about some numbers.
Yes.
That I remember.
Yeah.
Why don't you go on, because otherwise we'll miss the deadlines.
Yeah. So this was okay. So saying how would these simple cooperative techniques, hard fusion and AWGN combining, how would they work if we only had AWGN? And it has been shown, and we confirmed here, that even in only noise without any fading conditions, that even in case where you have only noise, they bring benefit. So having fusion bring benefits in noise environments itself. How much? We show that for hard fusion, switching from single sensor to using, it would be the red one, 2 out of 5 would be the best one for these settings. And for equal gain combining, of course, increasing the number of sensors in noise-only environment would bring a better performance. So what we did here is...
What was that? Was that a fading channel or...?
No, there was only noise.
Okay.
Environment only noise. So there's no fading at all.
So how do you explain that 2 out of 5 is the best one?
We did not actually come up with an explanation, but in the setting, which was, I did not include the numbers in the slides there, in the setting which was 200 milliwatts, 20 meter distance or similar, assuming that we have only noise, it just came up to that one. I would not, we did not actually explore why 2 out of 5 would be that one. Okay, so what we did here, after showing how it works in a noise only, we used an example of channel, vehicular environment channel, which was derived in the work that we reference here. It's a double slope channel model with a cutoff distance of 100 meters. And we liked it because there's plenty different vehicular channels that were derived and in different ways. We liked this one because it was made it was derived experimentally by having two cars running around different neighborhoods in different settings. And it was derived for constantly present signal, which was our assumption as well. So that's why we decided to go with this model. I included the parameters, and then they also showed how fading parameters depend on the distance. So we put these values in two scenarios. One would be infrastructure to vehicle, and another one vehicle to vehicle. In infrastructure to vehicle, we assume there's roadside transmitter and receivers who are trying to decide whether the signal is available or not. Looking in global, in this kind of topology, we have a situation where sensors have similar average signal-to-noise ratio, and the results of simulations for transmitter at 2 watt, distance between cars at 11 meters, and distance between this group of cars to the tower of 300 meters, low normal shadowing, and Nakagami fading in this setting for noise. And in order to obtain probability of false alarm of 0.01, we simulated, so this was a pure simulation, we simulated all 5 hard fusion techniques and equal gain combining. So the results show that in this setting where sensors have similar average signal-to-noise ratio, equal gain combining is the one that's the most favorable because it gives the best performance. And this actually this goes in line with what theory suggests, that equal gain combining should give a better result than hard fusion because it does create additional effort.
What does 1 out of 5 or mean?
If in hard fusion techniques, if 5 cars is
It's a voting technique.
it's a voting
So
technique.
one of them says,
So there's
One of
5
them says
sensors.
it's
yeah,
Yes. So it would be, or if any of these 5 say it's busy, that would comply.
so the way you can see this, right, all cars have the signal coming from the transmitter at some fade. So the signals are fading due to channel.
Geometric here is a Q miss. What is Q miss?
Probability of miss.
Probability of miss.
It's cooperative probability of miss. Usually instead of P miss, they use Q miss. But overall. So overall probability of miss for the overall system would be Q miss.
So this, you might want to also look at the probability of false alarm.
We actually here fix it.
What does that mean?
So we say the performance probability of detection for this setting, saying probability of false alarm would be 0.01.
How do you achieve that? How can you fix it?
Assuming that we know noise, which we do, we say that the noise complies to something like
Oh, you selected your threshold so that you get this.
Yes.
false
Yes.
alarm.
But that's only true for each signal, right? For when
Yes.
you do 1 out of 5, you're going to increase the false alarm probability quite a bit.
The question is like, if once you do cooperative, do you compute the false alarm for the
Yes.
cooperative?
Yes, yes. So it's a cooperative false alarm.
So if the threshold you use here for 1 out of 5 is different than the threshold
Yes.
you used in the single sensing scheme.
Yes. The threshold, actually, yes, that's correct.
It's a cooperative threshold.
Yeah. So in equal gain combining, that matters because the threshold is the one that's at the fusion center. In hard decision, it doesn't matter. Still, it will be the old threshold because each sensor decides for himself.
So 1 out of 5 was hard decision.
Yes.
Why does it not matter there?
Yeah.
Because there is no cooperative threshold. as a single value. Each sensor has its own
But when you
threshold.
do 1 out of 5, your false alarm probability doesn't increase.
Are you sure that's what you did? False alarm depends on the calibration.
It does. Yeah, it does actually. Actually,
I think you've done it so long ago that you might not remember it.
Yes, true.
My guess is you have false alarm for each signal set to 0.01, but cooperative false alarm is going to have some strange values which will tend to twist your curves if you normalize to that.
If you worked with Goran at that time, he probably told you to do the right thing, and that's a question that you should think about now.
I actually published this.
The fact that you published this, we should be silent about it.
But the other issue is that you have EGCs, it requires transmitting waveforms to a central site, so that could require a lot of bandwidth.
Yes, that's one of the
So it's
constraints.
probably unrealistic. It's a baseline, but it's unrealistic.
Yes.
Again, for EGC, you should sort of think of how many bits you want to quantize it to, what the quantizer you're going to use, and what's the overhead.
Yeah, but EGC, literally you have to take the full signal bandwidth and combine them.
No, he just sent the SNR.
Send the measurement.
It's a real number.
You only send this.
Yeah, only single number.
Only single number. It's not that bad.
I thought you were combining the waveforms and then threshold.
No. EGC, no.
We were adding that.
Actually, it's not that bad.
So we single measurement from each sensor is delivered to the fusion center. So it's a single number. It's not the addition of the whole
Then
waveform.
why is it called combining? Combining means the
I-
signals are combined in some coherent fashion, and then you get large gain, of course.
There's actually, like, you're very right. There are 3 levels of techniques: hard decision combining, statistics combining, and soft combining, like mine.
Yeah.
The soft combining with mine was unrealistic.
So you're only doing
Soft.
You're doing statistics combining.
statistical
Yeah,
combining. So
which
what?
is-
Explain to me what that is. I mean, your slides are too high level. You have to have some
Where's your EGC
diagram of
description?
the scheme.
I didn't put it on the slides.
You have it somewhere.
So how is?
Do you want me to?
How do you? I don't
Or
understand.
put it on the whiteboard.
Because I don't understand that. Because in one case you are integrating a signal and thresholding it.
Mhm.
So when you do statistical combining, what do you do?
So
Or you can also use the picture where you showed your energy.
yeah. Yeah.
So where do you combine?
We would be combining here. So this would be the value that would be being delivered to the fusion center.
You combine the integrator values
Yes.
are combined. But is there some side information also that you have to provide?
No, we did not consider.
He assumes that the noise level.
Is it the same at each place? Or?
Well, the temperature is same, noise is same area.
But then why will that help you? I mean, understand conceptually.
In the fading case, it helps because you
Yeah.
get 7
Because of-
energy, I get 7 energy.
Because of shadow fading.
Yeah, because
But
of
not.
that.
So there's some fading models in this.
Yeah, he just described.
This is the fading model. So we use a dual sub channel.
It's called Makagami fading. It's a 2-parameter fading model.
So, but somehow you have to normalize the joint threshold to the observed SNRs. If you have severe fading, you have more noise in the integral. So somehow you have to give weights to each of. If you're taking a new threshold, you just don't sum them up. Have some W1, S1, W2, S2, right?
In equal gain combining, these weights are 1. So it's the simplest, instead of putting weights by measuring SNR, then putting some weights to it. We were going here to be faster instead of estimating SNR, to be faster, just send the value and you can see, let's see how much it gains. So, moving from infrastructure to vehicle, another topology that we wanted to examine is vehicle to vehicle. We take again example of 5 sensors and transmitter being on one of the vehicles. Here, because vehicle that is the closest to the transmitter has the highest signal to noise ratio, and we show that in this case, of course, the most favorable fusion technique is OR technique, and for this setting of the distance between the cars, again, like 11 meters and transmitter power of 10 milliwatts, using again the same channel model. That's how much the benefit would be. The results of how this work would be that we wanted to show the balance that's needed, how to balance need for to do fast sensing of wideband. And since we saw that sensing of large bandwidth in a single sensor introduces more delay, if we employ cooperative sensing, we show that different topologies favor different fusion techniques, but the overall conclusion is that OR technique would be the one that would be a good alternative as an overall fusion technique for vehicular encompasses. Okay, do you have any questions for the first part? Or
Why not?
skip to the second?
So for the EGC,
Yes.
you need these energy values
Yes.
from all the cars and have them together.
Yes.
How much data is that?
How much data?
Yeah.
There is actually work around it where they suggested how having a level and knowing the number, how many bits does it actually take, and how much you lose if you decrease the number of bits. So instead of sending 8 bits, decrease to 3. And they actually showed that the 3 bits is perfectly enough.
For the EGC?
Yes.
So 3 bits per car.
Yes.
And we say 4 is good alternative.
Yes. It's 1 bit only.
Why do I care about 1 bit versus 3 bit?
Well, I guess what you haven't studied is like what is the rate that you have to update, which will reflect how fast the channel changes. You know, you went one step, and that one step is like how long does it take to measure the channel to get satisfactory performance. But you know, you have to like know the vehicular environment to, you know, somehow be able to tell how frequently the channel changes, so that you have to make the updates to be able to evaluate what's the overall throughput of the network, control network that will exchange the data. That would be an engineering step that Mark was referring to, and I think somebody like Toyota would be interested in that. He didn't, but that's about some.
For each packet that you send, you have some 50, 100 byte overhead. And then you add in the 3 bits. 50 bytes plus
We don't like
plus
that.
50 bytes plus 1 bit.
I don't like that overhead. You should invent things without that much overhead. You want to send 3
Okay,
bits and you send
let's
100
move
bits
on.
overhead.
So we have about 15 more minutes.
Wow,
Can you
okay.
convince
So
us
I'll
at
be
that
fast.
time
The
that
second
you-
part, actually, I expect the first part to be really fast. The second part is way more interesting.
So convince us at 15,
I'll be really
15
fast.
minutes that you did something.
So looking at this cooperative and looking at knowing the performance of a single channel, now we say, let's look at the example. Let's look at what the signal actually looks like in the vehicular environment. And looking at it, there is important notion of changing power level over time due to mobility, whether it's a sensor, transmitter, or the reflectors in between. So, looking at it, we said, let's try to come up with a sensing algorithm which would incorporate in it inherent property of the vehicular environment that the received signal power changes. And what we want to give as an output would be a spectrum activity vector, which would describe subband activity, saying where zero the subband is free and 1 is occupied. And of course the challenge, how to find it, and if the noise and received power levels are not known, and due to the changes in time. So it's example here, VPSK signal, because sensors and transmitters moved or reflectors moved. The occupancy vector didn't change, but the power level did change. So we want to look into this problem. So we're saying we have varying signal power at the cognitive radio front end, and it's due to the fact that either it's transmitter is moving or receiver is moving, or the reflectors are moving along the path. So what our goal is to have a low complexity algorithm. We do not want to exploit certain signal properties, so we're going with energy detector again. We want to incorporate in our system, in our model, power level variability, and we want to use maximum likelihood. The system would be applied for any vehicular environment, and since we would be applying maximum likelihood detection for a system where the values of all vectors, of activity vectors, will be equally probable, this kind of work would give an assessment of how any other technique would perform in a mobile environment. So, looking on the maximum likelihood estimation, just quick background, having the certain observations and the parameter that we want to observe. We are maximizing likelihood function, which is actually the system model, and say for the argument of the parameter which gives the maximum of the likelihood function will be the one that we say is the one in place, and maximum likelihood is widely used in different applications. It's mathematically efficient. It minimizes the overall probability of error. They're all when channel occupancy is detected, and has numerous applications.
I think you can skip this.
Yeah. So, motivation, again, as the signal power, as the environment changes, the signal power changes randomly. So we want to model this randomness of change. And we say we're going to be looking at this, looking at the system and assuming that this, for different time instances, as the environment is changing, assuming that this factor is not going to change, we will be looking at the system parameters which would affect the overall performance. So we're looking at the two types of fading, whether it's frequency selective or non-selective, and then we are looking at the changes, how frequently the power change, looking at the coherence time, which is approximately related in this way to Doppler shift. And what attracted us to it was the fact that it actually includes the relative speed between sensor and transmitter. So what we say we're calculating the periodogram, and here we say if we are picking the number of samples for each subband such that it equals coherence time divided by sampling time of our receiver. Looking at the M, we say it's a time, assuming that we're doing period calculation. Big assumption is that within one frequency bin, the power level doesn't change. The power level is constant. So that assumption would translate, looking at the coherence time, would translate in choosing number of samples for each subband to be such that the coherence time remains preserved. So looking at this calculation, we derive our model. First we did the data set creation to show how we create one data set for this system. So modeling each sample inside a subband, modeling each sample as activity times the square root of our received power level. And activity would be 0 or 1, depending on whether it's the primary signal or the signal we're looking for is present or not. And then we calculate the power for each frequency bin. Now, for each bin, we repeated capital K time instances in the subsequent time instances. So our goal is have the frequency being calculated at one time instance next, and then capital K times. Capital K would correlate to overall sensing time because it actually determines what the sensing time would be in this relation. So sensing time divided by m times the sampling time. Overall, the goal was to, for each time instance, create a vector which would describe power levels for each frequency bin, and then repeat it over time instances. So this kind of matrix would be the data set that we were beginning to work with. So now we in order to propose a system that we're using for detection of activity vector, we go with some assumptions. We say that we're observing certain number of channels over a certain number of sample sets, so we know what the K and capital I are, and we say that each sample set has capital M samples, received samples in Gaussian noise, and activity vector doesn't change over time. So we assume that, which is pretty reasonable assumption, because if we assume that overall sensing time is very short, the activity vector will not be changing, especially for the examples that we're using later on, which will be a TDT signal. So what we are saying is, mathematically, we say that what was received can be modeled as some power times activity and some noise. For the received power, we assume that it has certain known average power level and power variance. Also, for the power realizations, we assume that over for each k, they are independent and Gaussian. So each realization is. So now having this matrix, we did not employ a complex approach for using this power variance. We thought let's just average, assuming that we incorporated it into our calculation. Let's average over all time instances, and for each frequency bin, it would come to a model like this, where again we have a power with a slightly different variance than before, averaging over k time instances and the new noise. Then we say, let's switch this to vector notation, because we have multiple values of frequency bins. So we use this vector notation, where this will be the vector of observations of data, this will be the vector of activity, and then activity vector would actually turn into a diagonal matrix, and then Q would be the power levels that we're seeing. Overall, it would come up to this linear Gaussian model with certain distributions for noise. It's a typo, yeah. For power and for noise. So, sorry about the typo. Having this model, we want to, first we were thinking it's going to be a little bit complicated, but then it actually came down to a pretty feasible, mathematically feasible model, which we then wanted to break down by our system parameters. So assuming that our fading is frequency selective, for this model, we're looking for conditional expectation of observations depending on the activity vector. So we derive these expectations of covariance matrices for cases when the fading is selective and when fading is flat. Overall, this maximum likelihood problem translates into this maximization problem, where we have actually this multivariate Gaussian to be maximized all the values of activity vector. So looking at the examples, we said we're using an example of sensing 3 adjacent channels of NTSC TV spectrum. From 500 to 680 megahertz. And first, what we wanted to show is how this maximum likelihood algorithm would perform in a static case. So assuming that there is no power changes over time. So this would be the performance for 1 kilowatt transmitter, certain noise level, and the range of sensing times at 10 kilometer distance, and with this attenuation. After exploring static case, we moved first to a moving reflectors case. And Harris's work in WINLAB was, part of it was calculation of variance of the power, and showed it's up to 5 decibels. And here we assume that we have frequency selective fading, and say that for a range of power variances from 0.4 to 3 decibels, let's see how the system performs. So the blue curve would be the one without mobility, and as the stronger the power variance, the worse the performance. So this would be the one where, so moving from static case, we move to a mobility case where we have certain power variation. Then we say, knowing that this performance actually depends on the value, now introducing the mobility, we say the performance depends on the value of activity vector. And we wanted to see which one is the worst one. So going from 0, 0, 0 to looking at these 3 channels, going from 0, 0, 0 to 1, 1, 1, we see is the one that performs worse would be the 1, 1, 1. So we, in the future simulations, we use that value for activity vector to get us a lower bound of normal performance. Then moving, now knowing that we are, that we have, so we have a mobility, we have power change, we have value of the vector. We want to look the performance depending on the nature of the fading. So 2 extreme cases, one would be flat fading and another one would be frequency selective fading. So looking at it, frequency selective fading would be the one performing worse. So in the future simulations, we switch, saying to get a lower bound, we're going to be focusing on the frequency selective fading. Now, we wanted to, so knowing, having this setting, we wanted to translate this into speed of the sensor. And our goal was, if we know the sensor speed, or I mean, we generally it's a valid assumption, but knowing relative sensor speed would be a little rougher assumption. But assuming that we do know what the speed is, we say for this setting where we know what the carrier frequency is and where we know what the speed is, we can calculate the sensing time by multiplying the coherence time and a certain number of K's instances. So the coherence time would be the one determining what do we assume as when signal is constant, and then how many times we repeat that measurement to get the overall sensing time. So translating this velocity into power of miss, we say as the vehicle velocity increases, coherence time decreases, and overall sensing time decreases. Because we fixed K in this case, probability of miss overall gets increased with the sensor velocity. What matters here is, I mean, why we needed this curve, is the fact that if we start from opposite, if we want the probability of miss to be 10 to the minus 2, we can look at which combination of K and velocity would actually fulfill that probability of miss as a design requirement. Going forward, we translate it in something like this, where we say this is the sensor speed and sensing time for different combinations of K and so for each speed. So for each speed, for having a defined probability of miss, we can come up with decay that actually does fulfill that, that design requirement. So what we did is for different values of power variance, we say, let's see for the reasonable sensor speeds of reasonable speeds of the car. Let's see what the sensing time would be to obtain probability of miss of 0.01.
How do you explain the fact that the sensing time goes down with the sensor speed?
Because what we assumed is that we fixed k, so we fixed number of time instances that we are measuring over. And looking at this, it would be looking at the coherence time. Coherence time is that we don't go below, so it determines what the value of n is, value of sensing time for a single time instance. And then looking at the coherence time, because it's inverse proportional. Is that the word? Increasing velocity decreases coherence time. So for fixed k, increasing velocity, decreasing coherence time means that the n is getting smaller. And then for a fixed k, it means that the overall sensing time gets smaller. We could have, I mean, since there's several parameters that fit in, we started with m is fixed, determined by the coherence time. Let's say if k is fixed, how the performance is going to be. Another option would be, let's say, that the overall sensing time is fixed, and then tweak the value of k to how many time instances should we use. Okay. So what we showed in this work was keeping sensing time in this setting where we're sensing 2 channels of NTSC TV signal. Keeping sensing time below 1 millisecond would be a sufficient one for a full range. So it would be below for range of velocities, sensor velocities. Also, we say if the power variance is higher than 3 dB, which would correspond to the green one, for the same set of sensor speeds, we can actually go with the lower sensing time. And in that sense, we can say, knowing sensor speed, we can use that information and the performance that we want to achieve. We can use it to tweak the algorithm in a sense of determining having this huge chunk of data measured, how we should split it into how many time instance periods to actually get a better performance. And that was the main point of this second part. We proposed a system model, used maximum likelihood detection to examine its performance, used an example of 3 adjacent channels of NTSC signal, and we showed how the sensor speed information can be used to adapt the algorithm in place to gain better performance without changing anything else. So Do you have any questions?